Hi everyone, so I'm going to share my screen. So here I'm going to be talking about my recent paper on beyond perturbation theory in inflation. So I'm going to tell you briefly the main idea of the paper and also the main result. Okay. So let's get started. Usually when you do the calculation in perturbation theory in inflation, one uses the so-called informalism to compute the correlation function of some operator Q. And you use this master formula, you see that there is the time evolution operator from the early times to some later time eta. And then you have to evolve back to the early times by performing the anti-time order product. So in this formula, you see that one has to use also the I epsilon prescription in order to project to the Bunch-Davy vacuum. Okay. So suppose I wanted to use this formula to compute this 4-point function. Suppose I have this Lagrangian for zeta. Zeta is a primordial fluctuation or inflaton, if you want. And I have this interaction, self-interaction. And then suppose I wanted to compute this 4-point function and compare with the power spectrum squared. This is the typical value of the power spectrum of the primordial field. And it turns out that this parameter goes like GNL times P theta, where GNL is the typical parameter for non-Gaussianity of the 4-point function. And this things turns out to be just the lambda, the coupling constant of the theory. And as long as this lambda is less than 1, that means you are inside the perturbation theory. And the same goes for the 3-point function. If you have the cubic interaction, you can compute this 3-point function and compare it with the power spectrum to the 3/2. And then this turns out to be FNL times the square root of P theta, where FNL is again the parameter for the 3-point function. And as long as this parameter is less than 1, that means you are still in the validity of the perturbation theory. And the main point here is that the expansion parameter in perturbation theory is just the coupling constant lambda, okay, nothing else. And if you want to write down the distribution function of the primordial field in perturbation theory, you will start with the Gaussian piece plus some other corrections due to 3-point function, 4-point function, and so on. These are just the small deviation of being Gaussian. It's like you are exploring around the peak of the distribution. And if you want to know the expansion parameter in this case, you can just factorize the Gaussian piece out of all the terms. And it turns out that the expansion parameter in this case goes like FNL times theta, and it involves the side of the field. Okay. For the 3-point function, it involves the FNL times theta. And for the 4-point function, it turns out to be GNL times theta squared. So this theta dependence implies that if you're going to the tailor of the distribution like this, so suppose that if the value of theta is larger than 1 over FNL in this case, for the case of 3-point function, it means that you are going out of the validity of the perturbation theory. And that means that whatever calculation you wanted to do at the tail of the distribution, it has to be in a non-perturbative way. Okay, so it cannot be captured by perturbation theory, the usual perturbation theory, okay, because of this expansion parameter. So now we propose that the way to do the calculation at the tail of the distribution has to be in the semi-classical way. So we propose that because later on we are going to compute this object, the wave function of the universe, okay, and we are going to compute this object in the semi-classical limit, okay, because going to the tail meaning that you are going to have the unlikely events at the tails, okay. So you might ask the question that why we are interested in going to the tail of the distribution. So this has something to do with the primordial black hole formation, which typically happen around the horizon reentry. So for example, you can compute this object, the mass fraction of the PBH, which you have to integrate from the threshold theta state up to infinity. And usually this threshold is of order of unity. That means this beta, the mass fraction, is sensitive to the Taylor of this distribution P of theta hat. And this theta hat is the smoothed version of the primordial field. And remember that in perturbation theory, you have this expansion parameter, FNL times theta. And if theta is of order unity, that is it's just FNL. So that means if FNL is less than 1, that means you are still in the perturbation theory. But this is only the case for slower inflation. If you are in K inflation, where FNL is of order of 100, then that means you are going out of the perturbation theory. So in this sense, to study the primordial black hole, one needs to go beyond perturbation theory. So now let me just go to the case of inflation, and then let me start with the free theory. In this case, the wave function is defined in this way. And you know that the free solution for theta can be written in this way. And then you can just use this, the classical solution, plug it back in the action to compute the on-shell action. And it turns out that it gives you the quadratic. And at the end, the wave function of the universe in this case is just a Gaussian distribution. Okay. And in the interaction theory, you can do the perturbation theory. Suppose we are in perturbation theory first, and then you can expand the wave function of the universe in this way. And to obtain these coefficients of the wave function, you can compute the 3-level Witten diagrams. Okay, and these are related to the correlation function of theta at late times. But now we are not in perturbation theory, so let me just go on and then show you the recipe to compute the wave function of the universe in our case beyond perturbation theory. So in this case, you have to impose the boundary conditions, one at early times, the bunch Davies, and the other at late times, theta 0. And then you have to solve the classical nonlinear equation. And then after that, you use the solution and plug it back in the action to obtain this wave function of the universe in the semi-classical limit. And here we are interested in this coupling theta prime to the fourth. Okay, so here I skip the reason, the justification of this coupling. Okay, so this coupling has some advantages. So inside the horizon, you have the free theory, and then outside the horizon, close to the late time, you also back to the free theory regime. So this is the PDE, the differential equation for for this coupling, and then one has to solve this PDE subjected to this boundary condition. Okay. And here we choose the Gaussian profile at late times like this because it has something to do with the primordial black hole formation, because usually people assume the spherical symmetric configuration at late times in order to produce the primordial black hole. So this is a solution for small lambda, and this is a solution for large lambda. And of course, when lambda is small, you reduce to the perturbative result. Okay. And then after this, after we got the solution, we can plug it back in the action and then to compute the on-shell action. And in this case, the on-shell action turns out to proportional to lambda tilde to the 3/4. Sorry, lambda tilde is the lambda times theta 0 to the square. And it turns out that the wave function of the universe goes like e to the minus theta 0 to the 3/2. Okay. And then this implies that the wave function of the universe, the probability is the tail is thicker than the one of the Gaussian. And here is the future directions. So since now we obtain this wave function of the universe, and in principle, if you square this wave function, you are going to obtain the probability distribution function of such late time configuration. And then if you have to scan over all the late time configurations in order to obtain the distribution of the PBH formation. And we wanted to generalize this to other interactions, other fields, include the Sorrow inflation, include the tensor mode, and so on. And this would be the next step of our project. And here we wanted to explore some other limits of going beyond perturbation theory, namely the large number of lakes limit. And also we want to explore whether there is some implication in ADS CFT or not. Thank you for your attention. Thank you.